Okay. I'm sorry that I changed the title a little bit. The title on the website is too long, but the topic is the same. And I'm also sorry that I have talked about this last week in the off-workshop seminar. But I will try to include some new materials. So I will talk about a kind of percolation observable, which could be interpreted as a correlation function of some primary field in the percolation conformal field theory. And moreover, I will show that there exists logarithmic divergence in this observable. So in some sense, this confirms the belief that percolation CFT should be logarithmic. And this is based on a joint work with Federico Camia from New York University, Abu Dhabi, and the Korea Institute. So what is our model? We consider side percolation. Let me briefly recall its definition. Suppose we have a graph G, which is not necessarily finite, and a parameter P between 0 and 1. For each vertex, we assign a random variable omega v. These omega v are IID random variables. And with probability P, it takes value 1, and with probability 1 minus P, it takes value 0. When it equals 1, we say this vertex V is open, and otherwise, we say this vertex is closed. And in this talk, we focus on side percolation on the triangular lattice on the plane. Then there exists a critical value of the parameter P, which equals 1/2. So what does this mean? If we consider the probability that there exists an infinite open cluster, then this probability equals 1 when the parameter P is strictly bigger than 1/2, and this probability equals 0 when P is less than or equal to 1/2. And the critical case is particularly interesting. At criticality, the model is conformally invariant. There are many ways to interpret conform invariance. One way is to consider Cardy-Smirnov formula. So suppose we have a two-dimensional topological quad, which is a bounded simply connected domain with 4 marked points on its boundary. And this delta is the mesh size of the lattice. Now, and we take a discrete approximation of this quad, and we call it omega delta, and also 4 marked points in the discrete lattice. Now, in this lattice, we consider the probability that there exists an open path inside this omega delta, connecting the boundary segment x1 delta, x2 delta to the boundary segment x3 delta, x4 delta. Then this connection probability has a scaling limit when delta tends to 0. And moreover, this limit function P is conformally invariant. What does this mean? Take any conform map phi from omega onto another bounded simply connected domain, phi omega. Then we can also consider the connection probability inside this phi omega with marked points phi x1 to phi x4. It turns out that these two quantities are the same. So this is conform invariance. And moreover, if this omega is a nice domain, if it is a equilateral triangle with 3 vertices x1, x2, x3, so x4 is here, then this connection probability has a very nice formula. It simply equals the length of this part over the length of x3, x1. And this formula was first derived by Cardy in 1990s by regarding the function P as a correlation function of the degenerate field or the boundary condition changing operator phi 1, 2 at the 4 marked points. Then, according to some theories, some arguments in CFT, this function P should satisfy some second-order PDEs. And Cardy figured out this formula by solving those PDEs. And this formula was rigorously proven by Smirnov for side percolation on the triangular lattice in 2001. And this is a breakthrough in the mathematical study of two-dimensional statistical mechanics. Also, this function P can serve as an example of correlation function in the boundary percolation CFT. But my question is, can we say something about the box CFT? This is my first question. And moreover, it is believed that percolation CFT should be logarithmic, which means you should see logarithmic divergence in some correlation function when 2 points collide. So my second question is, can you see logarithms in your constructed observable? Now we start from the discrete side. We take n vertices in the scaled triangular lattice. Here's a direct but bad example. Recall the random variables omega v defining the model. These are IID random variables, and the most direct way is to consider the expectation of the product of those omegas. Since they are IID, so this simply equals 1/2 to the power of n, so it is trivial. Here's another option. Now we define a spin model on percolation clusters, and this definition is inspired by Edel-Sokol coupling between random cluster model and the post model. So suppose a percolation configuration is given, and let Ci be the collection of percolation clusters, and let sigma I be IID random variables with equal probability taking values 1 or -1. Then for each vertex, we define sigma of v to be sigma I if the vertex v is in the cluster Ci, and then we define sigma v to be 0 if v is closed. Well, it's clear from the definition that sigma and minus sigma has the same distribution. So when the number of points is odd, this spin correlation simply equals 0. But as long as n is not odd, this spin correlation can encode the connectivity properties of percolation. For instance, for the 2-point function, you can take just 1 minute to find it equals the probability that Z1 delta and Z2 delta are in the same open cluster. And I would like to use the physics notation to denote this spin correlation. And for general even number n, the spin correlation could also be expressed as a linear combination of point-to-point connection probabilities. For example, for this 4-point function, is the sum of these 4 probabilities. The first term corresponds to the probability that 4 points are in the same open cluster, and the remaining 3 terms correspond to the probability that 2 points are in the same cluster and the remaining 2 are in a different cluster. So roughly speaking, this correlation function equals the probability that each marked point is contained in some macroscopic open cluster. So if the scaling limit of this spin correlation exists, we may interpret it as a correlation function of the density operator, which measures the cluster density. And fortunately, it has a non-trivial scaling limit when delta tends to 0. So we let each Zj delta tend to some Zj in the complex plane, and those Zj are distinct. Then according to work by Federico Camia in 2024, this spin correlation will normalize probably by this pi delta to the power of -n. Then it has a positive and finite scaling limit. This normalization term is of the order delta to the power of 5/48 plus a little over 1 term. And this weird number is the one-arm exponent in percolation, and you can just ignore it in this talk. Moreover, this spin correlation in the continuum is Mobius covariant. What does this mean? So for any non-constant Mobius map phi of the complex plane, as long as it does not map any of the marked point to infinity, we can define the sigma correlation at phi x1, phi x2 to phi xn to phi zn. Then this spin correlation equals the spin correlation at z1 to zn times absolute values of the product of some derivatives of the conformal map to a certain power. Yeah, and actually, the connection probabilities contributing to this spin correlation also have non-trivial scaling limit when you're normalized by the same term. For instance, you can define these quantities in the continuum. And they also satisfy the conformal covariance rule in equation 1. And we know a Mobius map can fix 3 points in the complex plane. So as a direct consequence of this Mobius covariance, we actually know the functional expressions of the 2-point and 3-point functions. There are basically just some powers between the distance of points. So, in particular, if we consider the ratio of the 3-point function over the square root of the product of 2-point functions, this is a universal constant. And actually, there is a prediction from the physics side of this constant, which is known as the Fino-Vita formula. And the mathematical proof of this formula may be forthcoming using Liouville quantum gravity techniques by Xin Sun and several other persons. So we already have a nice observable. Now let us come to my second question. Where can we see logs? From this equation, for 2-point or 3-point functions, there is no log. So we should start at least from the 4-point function. And fortunately, we can see log in the 4-point function. And this is our main theorem. So if we let z1 and z2 tend to a single point, then the 4-point spin correlation has this asymptotic expansion. We have the first 3 leading terms, and the leading term is the product of 2-point functions. And there is log in the sub-leading term. This constant C1 is just the constant in the 2-point function. And this CL is a positive constant, and the C0 is a real constant. And this function f is also explicit. Yeah. I have several remarks. For boundary FT, it is not technically difficult to see logarithms. Because you have BBZ equations, you can see log by solving those equations. Actually, one could find logarithms in a boundary FT at any central charge. But for the box FT, the situation is different. You don't have degenerate fields, so in general, you don't have BBZ equations. And they are harder to study, but nevertheless, this is evidence that bulk percolation CFT is also logarithmic. And for the bulk CFT, logarithmic nature is really special for percolation. Maybe some other models have, but it does not. Not every model is logarithmic. For instance, if we consider FK easing instead of percolation, then we can also define the spin field, which is just easing. And for easing, we know the spin correlation very well due to Cherkag, Honger, and Yuzurov. For instance, in the 4-point function, there are basically some polynomials. And from this formula, there's no log. Even if you add more points here, we still can't see logs. And I don't know whether this is true. Several weeks ago, one physicist showed me a formula he predicted for post model of this 4-point function, and in that formula, if he is true, there is no log as long as q does not equal to 1. And the percolation is a post model with q equals 1. In that formula, if you let q tend to 1, you will see log. And as I said before, this spin correlation can also be interpreted as the correlation function of the density field psi at those points. And this theorem is suggestive of the following operator product expansion of two density fields. So in this OPE, there are two new fields, phi and phi hat. There are two distinct fields with the same scaling dimension, 5/4. And actually, we also have probability interpretation of these two fields in the discrete, but I don't have time to discuss it. It seems natural to identify the new field phi with the energy operator and phi hat with the so-called two-cluster operator discussed by Cardi in 2013. Yeah. Here are several remarks about the proof. I talked about the proof last week. So recall that the spin correlation could be expressed as a linear combination of connection probabilities. And in the first step of our proof, we use independence of percolation to decompose those connection probabilities into logarithmic terms in some way. And this step only works for percolation because at some places, independence is crucial. And in the second step, we use conformal invariance of the model to show each term in the first step basically have the same order. So when you add them up, you see a logarithmic correction. And at least for percolation, this argument could be used to analyze other observables to get logarithmic correction. And I have a final remark. Yeah. Several lower quantum gravity people told me last week, based on the decomposition of connection probabilities in our argument, they might be able to use LQG techniques to compute the structure constant. They may be able to compute the constant CL and C0 over C1 to the power of 2. Yeah. And that's all. Here are some related references.